What if the most toxic environmental disaster in the United States, the kind of pollution that kills rivers and stains entire landscapes, is actually hiding the key to our highest tech national security needs?
It's a wild thought, but it's not a hypothetical. Something strange happens when you look closely at these polluted creeks.
That's been very strange.
They might just hold the key to America's domestic supply of critical rare earth metals.
And we are not talking about just any components. We are talking about the absolute cutting edge, the super strong heat-resistant magnets in an F-35 fighter jet,
The high-performance motors driving electric vehicles.
the sophisticated guidance systems for missile defense, and the raw materials for all this stuff are being discovered not in some traditional dusty mine pit, but flowing right out of what looks for all the world like toxic orange waste.
Yeah, for decades, that orange water was seen as, well, purely an economic drain and an environmental curse. It was a symbol of industrial debt.
A really ugly one at that.
A very ugly one. But now, through some really remarkable engineering and chemistry, that same liquid is being reframed as a massive national strategic asset.
Okay, let's unpack this. We are diving deep into the world of rare earth elements, or REEs, and the startling discovery of significant commercially viable concentrations found in this highly acidic water.
Water known as acid mine drainage, or AMD.
And our focus today is primarily on the Appalachian Basin, a region, long plagued by the legacy of coal.
And we should probably clarify what rare earth elements are for a second. They are a critical group of 17 metals. They're indispensable for modern technology because of their unique magnetic and phosphorescent property.
And catalytic properties too, right?
Exactly. And the sources we're looking at highlight one in particular, yttrium oxide, which is essential for everything from specialized lasers to satellite guidance systems. The U.S. reliance on foreign sources for these has become, well, simply put, a massive vulnerability.
To really get the potential of this discovery, you have to picture the scene of the pollution itself. We need to go to northern West Virginia.
Right, to the area around Deckers Creek.
What did that look like before all of this?
Well, I recall reading the descriptions given by locals who grew up there, and they paint a pretty brutal picture. For stretches, the creek ran a harsh, unnatural, chemical orange color.
Not just a little discoloration.
Oh, no. A deep, rusty orange. If you stood on the banks, the rocks were stained permanently red and brown, sometimes almost black, and there was this constant, sharp, metallic smell hanging in the air.
You could smell it.
You could absolutely smell it. It wasn't the smell of nature, it was the smell of active corrosion.
And locals, they had a name for it. They remember portions of that creek as a cesspool.
A total cesspool. There was no aquatic life, no fish, very few insects. It was a visual cue of long-term environmental failure, the lingering cost of the coal industry.
But here's the fascinating part. That specific visual blight, that harsh acidity, that unusual color, that was the very first clue that an incredibly powerful chemistry was already at work.
Right. It was dissolving and mobilizing critical metals most people had never even heard of.
The acid had already done the hardest part of the job.
It really had.
So our mission today is to outline how visionary scientists and engineers managed to harvest strategic, high-purity metals from this environmental nightmare. We will detail the sophisticated, custom-built engineering required for the process, and then place this American technological breakthrough into the high-stakes geopolitical contest against China's global monopoly.
It's a deep dive into chemistry, engineering innovation, and national security, all flowing down the same acidic stream.
Before we go further, make sure to hit subscribe and support the deep dive. So let's start at the beginning. We have to understand the root cause. The curse of acid mine drainage, or AMD, across Appalachia. For listeners who might not be familiar with the geography or the history, how did this environmental catastrophe even begin?
The source is almost universally abandoned coal mines. You have to picture the process. When mining companies dug tunnels deep into the Appalachian rock formations, they cut through seams of coal, but in doing so, they also exposed massive amounts of the surrounding rock to air and water.
So they created all these new surfaces inside the earth.
Billions of square feet of new surface area. And when operations ceased and the companies, walked away, those long walls and huge piles of broken stone were just left behind in the tunnels. Forever.
And within that rock, you have the key culprit, a mineral that looks deceptively innocuous.
Pyrite.
Pyrite.
The classic fool's gold, exactly. Pyrite is an iron sulfide mineral. And by itself, it's harmless. But once that broken stone is exposed to the unique combination of both air oxygen and water, which is inevitable in an abandoned subterranean tunnel.
Which is always going to happen.
It's always going to happen. A slow, relentless, self-sustaining chemical reaction begins.
And that interaction between the iron sulfide, the water, and the oxygen in the air, that's what generates the acid.
It basically turns the entire abandoned mine into a chemical reactor.
Wow.
Correct. Through a process called the pyrite oxidation reaction, the materials react to create concentrated sulfuric acid. This acid then becomes a super powerful solvent or leaching agent.
So it just eats away at everything around it.
It eats into all the surrounding rock, the soil, the tunnel walls, and it just drags out whatever metals are present in the geology. The final output is that bright, orange, highly acidic liquid we call acid mine drainage.
Yeah, it just pours perpetually out of old mine entrances.
Pours out, seeps out, polluting every creek and stream it touches.
And this isn't just a short-term cleanup problem. We're talking about a problem that lasts for generations.
Oh, precisely. The sources we've seen emphasize that this drainage continues for decades, sometimes even centuries after a mine shuts down, because water keeps flowing through those exposed piles and tunnels.
It never stops.
It never stops. For generations, AMD was treated only as a liability. It destroyed local habitats, made drinking water unusable, severely corroded municipal pipes, and was just a constant economic drag on the entire region.
So here's the absolute twist. That environmental problem, that sulfuric acid, that is what creates the strategic resource.
That's the key.
In a normal stream, where the water is neutral, a pH of around 7, let's say, rare earth elements are extremely stable. They are locked firmly into rock or sediment.
Completely immobile. They don't go anywhere.
But the very low pH of AMD changes the fundamental chemistry.
It changes everything. The acid created by that initial pyrite reaction is so aggressive that it strips metals from the rock that would otherwise never move. The AMD water doesn't just pull out the obvious pollutants like iron and aluminum.
Right.
It also pulls out those 17 rare earth elements, allowing them to remain dissolved, active, and mobile in the highly acidic liquid.
So the dirtiest water, the red, rusty, harsh-smelling flow, is literally the evidence of nature pre-processing the ore for us.
It's nature doing the first and hardest step of mining. Think about traditional rare earth mining. It requires massive blasting, crushing tons and tons of rock.
Huge amounts of energy.
Exactly. And then often soaking that powdered rock in strong chemicals just to begin the release process. In the AMD stream, the abandoned tunnels have done the digging, and the slow geological process has provided the crushing and the initial acidic dissolution.
And it sends the metals to the surface in liquid form.
Concentrated by the decades, already in a solution.
Now, what's critically important here is which rare earth elements are being concentrated. We keep mentioning that the AMD sludge is rich in heavy rare earth elements, or REEs. Why does this type of mining concentrate those heavy elements specifically versus the more common light ones?
That's a great question. And it's where the geological context of Appalachia meets the chemistry of the acid. Appalachian coal deposits are often associated with shales and fire clays.
Okay.
And those shales and clays just happen to contain naturally elevated concentrations of REEs, such as dysprosium and terbium.
So the good stuff was already there.
The good stuff was already in the rock. When the sulfuric acid leaches the rock, studies show that REEs are more readily dissolved and they remain more stable in that extremely low pH environment than some of the light rare earth elements, the LREs.
So the geological content of the rock, combined with the extreme solvent power of the AMD, naturally enriches the resulting toxic water in the elements we need most for defense technology.
It's basically a targeted chemical dissolution. This means that the product coming out of these treatment plants is already inherently more valuable than the average global rare earth ore.
Which is often rich in the light ones.
Right, which is often abundant in LREs like cerium, but really poor in HREs. This is why the discovery is so strategic.
Let's try to quantify this discovery, because the scale is what makes this a national game changer. This isn't just a little pilot project in a single stream.
Oh no, the total potential output is truly enormous. Researchers with the U.S. Geological Survey estimated that the collective AMD outflows in the entire Appalachian Basin carry roughly, and this is a quote, 1 million to several million pounds of rare earth elements and yttrium annually.
1 million to several million pounds a year.
Annually. And that is a conservative yet astonishing estimate based only on the current known outflows.
So when you put that number into the context of U.S. demand, This becomes a strategic imperative. It's not just an academic curiosity anymore.
Absolutely not. That estimated range, 1 million to several million pounds, could equal anywhere from a tenth to almost half of the typical annual U.S. rare earth consumption.
Wow.
Now, this won't solve 100% of our need overnight, but it provides a massive, stable, and domestically controlled foundation for our future supply.
What this fundamentally means is that these polluted creeks, these constant drainage flows, are acting like a network of, well, of man-made ore bodies.
That's a perfect way to put it.
And critically, they refill themselves continually as long as the mine water keeps flowing.
They are essentially being leached of their valuable content automatically every minute of every day.
Without the need for new disruptive mining permits.
And this reframes the investment proposition entirely. Before, building a treatment facility was a necessary, expensive environmental cost, a burden. Now, that same necessary infrastructure can be viewed as the extraction head of a massive, distributed, and essentially self-sustaining mining operation.
That's a huge difference.
A massive difference. Extracting from a waste stream versus crushing hard rock. It has huge economic implications, which I think we'll need to detail when we discuss the refinement process.
If this perspective feels useful, take a second to subscribe to the deep dive. It genuinely pushes us to keep bringing more research stories. Okay, let's zoom in on a specific location to see this transition from pollution to profit. Let's look at Decker's Creek and the Richard mine site.
Which was known as one of the worst sources of mine discharge in the area. It was constantly leaking this foul, low pH water.
So the first goal was, and I guess it remains, environmental cleanup.
It has to be. The state and federal governments funded a large treatment plant at Richard Mine in the mid-2020s. And the process was standard at the time, using lime slurry to raise the pH.
Which forces the iron and other bulk metals to precipitate out.
Right. It cleans the water and allows aquatic, lifelike trout to return. That was the mandated goal. That was success.
But when scientists from West Virginia University's Water Research Institute studied these existing cleanup sites, they looked past the clean water exiting the plant.
They focused on the waste product, the wet orange mud or sludge that settled in the bottom of the holding ponds after the cleanup.
And what did they find in that sludge?
They realized that while the existing cleanup process was successful at restoring the stream, it was inadvertently creating a stockpile of rare earth-rich feedstock.
Yeah.
Their analysis showed that sludge from these AMD sites could hold anywhere from 1.5 to 2 pounds of rare earths per ton of dry material.
So what's the significance of that figure, 1.5 to 2 pounds per ton? How good is that?
It is remarkably high. In traditional mining, getting a concentration that high requires intensive processing. This waste sludge right off the bat matches or even beats the grade of some overseas hard rock rare earth mines.
That's a game changer.
It's a total game changer because the two most expensive and environmentally damaging steps of mining, the digging and the crushing, have already been eliminated. They are starting with a material that is already highly concentrated.
This means the simple act of cleaning the water, which society has to fund anyway to fulfill its environmental obligations.
It creates a competitive, valuable product.
That's the economic bridge we needed to hear about.
It is. The capital expenditure, the CapEx, for a traditional rare earth mine is astronomical. You have to build facilities for crushing millions of tons of rock and dealing with massive tailings ponds. Here, the initial CapEx is already tied to environmental restoration funds.
Which makes the extraction aspect incredibly economically efficient by comparison.
Much more efficient.
Okay, so turning that pre-concentrated toxic sludge into high-purity powder is where the deep engineering innovation comes in. It's one thing to find the metals, it's another to refine them to 98% purity.
Which is what defense and high-tech suppliers actually demand. You can't sell them mud.
Right.
Absolutely. So the starting point for any AMD treatment plant is to use that lime slurry, a basic alkaline powder, to raise the water's pH. When the pH increases, the dissolved metal ions lose their solubility and they precipitate.
They turn into solids.
And settle out as sludge. Historically, this was a single step. Add lime until the water is clean. Simple.
But the WVU team realized that the traditional one-step process was actually, well, it was burying the valuable rare earths in a massive amount of low-value junk.
Precisely. A massive amount of iron and aluminum waste. So they developed a crucial innovation built on the concept of selective precipitation.
Selective precipitation.
The two-step pH process. It's specifically designed to separate the highly abundant junk metals from the much more valuable rare earths. And this requires very precise chemical control.
So walk us through those two selective steps. Why do the metals behave differently?
Think of it like a highly controlled sequence of filtration. In the first crucial step, they raise the pH only slightly, just up to around 4.5.
4.5, okay.
What's fascinating here is that the chemistry of iron and aluminum is such that they precipitate very quickly at these relatively low pH levels. Huge amounts of iron and aluminum fall out of the water and settle into a low-value sludge stream.
But the rare earths don't.
Crucially, the rare earth metal ions, particularly the desired REEs, are chemically resistant to precipitation at this level. They remain dissolved, they stay mobile in the water.
So they're using chemistry to filter out 90% of the unwanted bulk waste first.
Exactly.
Leaving the high-value rare earths dissolved in the liquid, ready for the next stage.
Exactly. Then comes the second step. Once the water has been largely stripped of iron and aluminum, they push the pH much higher, way up around 8.5. This higher alkalinity finally causes the rare earths, along with co-products like zinc and cobalt, to drop out of the solution.
And by separating the process into these two discrete, chemically tuned steps,
they isolate the REE-rich stream, resulting in a much thicker, heavier sludge that holds up to 2 pounds of REs per ton.
And this optimization is engineered directly into the infrastructure at a place like Richard Mine.
Yes, it's built right in. The engineering allows for two simultaneous processes: environmental cleanup of the iron and resource creation from the rare earth concentrate. The regular sludge from the first step goes to waste storage. The rare earth-rich stream from the second step is guarded carefully.
And to get that REE feedstock ready for transport to the final refinery, they use those fascinating long white fabric tubes.
The geoexile bags.
Right. What are those?
They are essentially giant, heavy-duty filters designed to dewater the sludge. They pump the heavy RE-rich mixture into these incredibly long fabric tubes. Over weeks, the water slowly drains out through the cloth.
And it leaves behind a thick, dense, high-grade mud,
which transforms a sloshy liquid into a compact, easy-to-ship pre-concentrate.
That's the key logistical step, I imagine.
It is. This dried mud can hold 1 to 2% rare earth metals by weight, a monumental jump in concentration from the original water. And it's important to note the financial commitment here. The Richard Mine infrastructure alone has cost over $9 million.
Wow.
Mostly funded by federal infrastructure programs and state reclamation funds. This isn't small science. This is a serious long-term commitment to dual-purpose infrastructure.
So this pre-concentrate then moves on to the final stage of purification. This happens at the specialized pilot plant at WVU, which is funded by the U.S. Department of Energy to secure this domestic supply route.
And this is where we hit the most complex part of REE processing, turning that mud into a 98% pure commercial-grade powder using something called solvent extraction.
Why is this step so difficult?
Well, this step is technically demanding because you're not just separating rare earths from junk metals anymore. Now you are separating the 17 rare earth elements from each other. And these elements are chemically almost identical. That's why their separation is the most difficult and expensive part of the entire global supply chain.
So before they can sort them, they have to get them back into a liquid state, right?
Exactly. The first substep is reliquefying. They take that dried, pre-concentrated sludge and mix it with a mild, hot, acid-like hydrochloric acid inside heated industrial tanks. This vigorous, controlled dissolution pulls all the rare earths and the remaining co-products back into a strong liquid solution.
So now they have their concentrated acidic soup containing everything.
Everything.
Now comes the actual sorting using solvent extraction. We need a simple explanation for this because the process can sound, well, overwhelming.
Let's use the oil and water analogy. They use two liquids that fundamentally do not mix. One is the water-based solution holding all the concentrated metals.
The soup.
The soup. The other is an oil-like liquid called the organic phase, which contains specialized chemical extractants. And this organic liquid has been precisely tuned to only bond with and grab the specific rare earth ions they were trying to isolate while ignoring everything else.
That was like a targeted chemical fishing hook.
That's a perfect analogy. And since they are separating 17 different chemically similar metals, say separating neodymium from praseodymium and then separating both from dysprosium, they can't just do this once.
Right.
Solvent extraction is not a single tank, but a cascade, often requiring dozens, even hundreds of tanks arranged in a long line. They're often called mixer settlers.
Okay, so explain how that cascade works to achieve the purity they need.
In the mixer-settler cascade, the two liquids are mixed vigorously in the first stage. This allows the target REE to jump from the water stream into the oil-based stream.
The fishing hook grabs it.
The hook grabs it. Then the mixture enters the settler area, where gravity forces the oil and water layers to separate cleanly. The now rare earth-rich oil layer moves to the next tank, and the slightly less valuable water layer moves backwards down the line, which increases efficiency.
And this mixing, settling, and moving process is repeated dozens and dozens of times.
Over and over. And each stage in that long line is tuned to peel off a different element, allowing them to achieve commercial-grade purity for each one.
So the genius of it is that one section of the cascade might be chemically optimized to capture the heavy rare earths, like dysprosium.
And a later section is tuned to isolate the medium rare earths. After many, many stages, the specific rare earth element they are targeting is securely captured in the oil-based flow, having left nearly all the impurities and other rare earths behind.
And what's the final step to get the actual powder?
Once the REE is isolated in the oil, they perform a final chemical flip, which is called stripping. They wash that purified, oil-based liquid with the clean acidic solution, which pulls the isolated rare earth ions back out into a clean water stream.
So it releases from the hook.
It releases from the hook. And because the impurities were left behind in the previous stages, this new water stream is extremely pure. After evaporating the water and completing some final high-temperature chemical steps, what remains is the valuable purified powder called rare earth oxide.
And the purity levels being achieved in these pilot systems, around 98% by weight, is high enough for commercial and defense applications.
It proves the concept.
From a toxic creek in West Virginia, you can generate a high-tech strategic powder.
And again, the critical detail here is that this process is particularly efficient at extracting the heavy rare earth elements, dysprosium, terbium, the very elements the global supply chain struggles most to provide.
So we have domestic proven technology extracting the most valuable resource from a waste stream that must be treated anyway. This takes us directly into the massive geopolitical context, the clash with China, which currently controls this entire market.
Well, the problem for the U.S. is systemic.
Yeah.
For decades, the U.S. operated under the assumption that these critical metals would always be readily available globally, cheap and easy to acquire.
We outsourced it.
We completely outsourced it. We had the expertise and the geology, but we shut down most of our own processing plants, choosing instead to import finished materials.
And the numbers on that reliance are absolutely damning. From 2020 through 2023, data shows that about 70% of all rare earth compounds and metals used in the United States came directly from China.
70%. And China's dominance is total. It controls the entire supply chain, not just the raw dirt. They produce roughly 70% of the global rare earth ore, nearly 90% of the required processing chemicals.
And critically,
more than 90% of the finished high-power rare earth magnets used in electronics and defense.
it's a single massive point of failure for advanced technology globally. We even see this paradox in California, right? The one major U.S. rare earth mine, Mountain Pass, historically shipped most of its concentrate overseas.
Often back to China.
Back to China, because the sophisticated processing was not available or competitive at home, Washington realized, maybe too late, that a huge part of its military and economic future rested on supply lines it couldn't control.
And this raises the critical question. What happens when a country with that kind of comprehensive control decides to use it as geopolitical leverage?
And they have.
Beijing has already demonstrated repeatedly that it is absolutely willing to weaponize its supply chain dominance.
So let's detail the specifics of that weaponization. Think back to 2025. In response to increasing U.S. pressure and tariffs, China didn't retaliate with tariffs of its own. Instead, they hit where it hurts most.
On April 4th, 2025, they imposed new, severe export controls on 7 key rare earth categories. These included the crucial heavy and medium elements like samarium, terbium, and, yes, dysprosium.
The exact elements being concentrated in the AMD sludge.
The very same ones.
Yeah.
And export controls are a choke point. They mean that any company wishing to send those specific metals or products containing them out of China must obtain a special government license.
A license which officials can deny, delay, or just stall indefinitely based on geopolitical priorities.
And the impact was immediate and chilling for global manufacturing.
Within just a few months of those new rules, Chinese exports of certain essential rare earth magnets Magnets used in everything from medical equipment to specialized aerospace sensors dropped by a shocking 75%.
75%. That immediately created global supply trouble. Automakers across Europe, Japan, and the United States reported massive disruptions. Industry groups in Germany and the UK warned that production lines were close to shutting down.
Because they couldn't secure the necessary finished magnets for their electric motors.
Exactly. Factories went into full crisis mode, just desperately searching for new, non-Chinese sources.
And China didn't stop there. They tightened the grip later that same year. In October 2025, Beijing added even tougher, more insidious regulations.
These new rules didn't just cover the physical metals, they covered the knowledge itself.
The intellectual property.
It was an attempt to lock down the intellectual capital. These rules required government approval to export technology related to mining, processing, recycling, or magnet making. They also severely restricted Chinese companies and citizens from helping build foreign processing plants.
So they are not only limiting the output of the physical material, but they are trying to lock down the engineering expertise and the technological know-how required to build a competing supply chain anywhere else in the world.
It's a strategic lockdown of the entire ecosystem, and you have to consider the strategic value of the heavy rare earths being targeted. Dysprosium, for example, is essential for neodymium iron boron magnets to retain their strength at high temperatures.
And where do you need magnets that work at extreme temperatures?
In the motors of fighter jets like the F-35 and in critical components of missile guidance systems, terbium is vital for specialized electronics and certain laser applications. These are core components of U.S. defense capabilities.
The sheer economic volume they were controlling is staggering. In the year before the controls, China exported nearly $3 billion worth of rare earth magnets.
$3 billion.
When a single country with that level of influence starts using export restrictions and knowledge barriers as tools in global disputes, every dependent nation must take notice and find alternatives.
And regardless of whether China sees these actions as defensive or aggressive, the message to Western governments is undeniable. Dependency equals vulnerability.
This is exactly why the story of the polluted creek in West Virginia stops being a regional cleanup story.
It becomes the heart of a much larger national strategy.
Absolutely. The acid mine drainage projects in West Virginia, coupled with pilot testing now happening at sites like the Berkeley Pit in Montana, are no longer viewed merely as scientific endeavors. They are officially integrated pieces of a national strategy aimed at rebuilding domestic supply resilience.
West Virginia University and the Department of Energy are speaking openly about this, about turning AMD from a chronic regional problem into a domestic rare earth source necessary for national security.
The goal is explicit: to build a predictable, technologically advanced domestic rare earth source that no foreign government can interrupt or block with a license control.
And let's connect this back to our earlier point. The AMD sludges are particularly rich in heavy rare earths, dysprosium, and terbium. These are the elements that are both the hardest to supply globally and the elements China specifically targeted in its 2025 export controls.
So this domestic source is designed to target the exact supply chain choke points that China created.
It's a direct counter. And what's fascinating here is that the U.S. strategy isn't trying to beat China on price for standard light rare earths, which China can produce cheaply and in massive volume.
No.
Instead, the U.S. is focusing its domestic efforts on extracting the REEs, the highest value, most strategically critical materials, from an existing liability.
It's a very smart use of innovation to address a specific acute vulnerability. The U.S. is essentially capitalizing on its industrial legacy, even the toxic parts of it, to create a future supply chain that is resistant to geopolitical pressure.
And if we connect this to the broader pattern, this kind of innovation turning environmental cleanup into strategic resource generation is not limited to the Appalachian coal fields.
This is a national model.
It is. Similar studies near Idaho Springs in Colorado show similar potential in water draining from old hard rock mines. And most notably, the same two-step pH chemistry developed by the WVU team is being tested at the Berkeley Pit in Butte, Montana.
For those unfamiliar, the Berkeley Pit is an enormous, infamous, toxic lake left over from decades of copper mining.
It holds tens of billions of gallons of highly acidic, metal-laden water.
It's an environmental Superfund site that must be monitored and treated indefinitely.
But the core principle applies. The water, which must be treated anyway, already contains concentrated, valuable metals. Instead of just treating it to meet environmental standards, Engineers are now looking at it as a giant, permanent resource body that feeds the purification infrastructure.
So we've come full circle. A decades-long regional environmental disaster acid mine drainage has been reimagined by chemists and engineers into a strategic national asset
One capable of challenging a global supply monopoly.
and securing the supply of materials necessary for the future of green energy and defense technology.
It's an incredible narrative arc. It proves that sometimes the solution to a national security problem lies not in digging a new hole in pristine wilderness, but in cleaning up the messes we already made.
Transforming liability into leverage.
Exactly.
This brings us to a final provocative thought for you to consider about infrastructure and value. The AMD treatment plants, like the Richard Mine facility, were built originally as an environmental necessity. They were funded by state and federal debt obligations.
They were expensive necessities that had to run for decades just to maintain stream health. That was their only job.
Yeah, those same permanent pieces of infrastructure, which must run constantly regardless of commodity prices to uphold environmental standards, are simultaneously producing materials worth millions
Specifically those crucial heavy rare earths.
and directly bolstering national security. So the question is, what other long-running, expensive, and necessary cleanup problems, waste streams, old industrial sites, or permanent reclamation projects might be hiding equally vital resources?
Resources that, if properly engineered, could transform from environmental liabilities into strategic national assets.
The key seems to be in recognizing that the pollution itself is evidence of powerful, pre-processing chemistry already at work.
That shift in perception from waste to resource is the new frontier of extraction and sustainability.
So how do you see it? Drop your thoughts in the comments, and if you haven't subscribed yet, join the deep dive so you don't miss the next insight.